like to share. We're here a second ago.
David, I think I can go second and I can share my slide with somebody because I'm not able to share. Yeah.
Okay. Okay. So Amanda, would you like to go ahead and go?
Yeah, I'm happy to.
All right.
Okay, let me share. Okay, let me just get this up. Can you all hear me and see my screen okay?
We can. Full
Great.
screen and everything.
Perfect. So I was a student in our Edison's lab, and today I'm just going to be sharing a bit about how we structured our project to address batch effects in large-scale metabolomics studies in order for us to identify stable spectral features to move forward with in the compound identification process. Here we go. Okay, so like many of you, oops, there we go. We want to identify endometabolites. And so the first thing we really had to do was to develop a reliable pipeline that would allow us to reduce all the variation that we have in our studies to be able to do this. So this is work that I have been co-authoring with Brianna Garcia, who's also on this call, where we designed 3 separate C. elegans studies to be able to link metabolic variation across all these different strains. So we had these 3 different groups of natural strains, central metabolism mutants, and UGT mutants that we grew in what we're calling an anchor design, along with anchor samples in a sample growth process that I'll describe in a second, where we then collected various chemical data, both NMR and LCMS data, to ultimately identify our significant spectral features that we wanted to move forward with in our compound identification process. So today I really want to show how we set up our experimental design, because we really did spend a lot of time and made some thoughtful decisions on how to do this appropriately so we could compare our data now in these 3 studies and in future studies that we are currently running. So first, we grew every single test sample from those 3 study groups alongside a PD1074 anchor sample, and we paired those by harvest date, which allowed us to capture any growth variation that we may have introduced in our study. We then extracted those samples by batch, and we added at this time an iterative batch averaging method that Art has talked about in the past, which allowed us to help us capture extraction variation. And then we also added, we ran all those samples by batch. We had 6 total batches in 3 sets, where we then added in pooled test samples and pooled anchored samples along with library standards. So when we combine A, B, and C, it kind of gives us this formula here down for batch effect, where we are able to capture effectively growth variation, extraction variation, and instrument variation so that we could walk away with reliable biological information. So after we did all that, we were able to pool these anchor samples because we did have so many replicates of our anchor sample at every step of the way. We then aligned all of those and selected only stable features that were present in every single sample. So again, those are biological features we can compare all of our test samples to here and in future experiments. After those stable features were selected, we then have done a meta-analysis that allowed us to look at the effect sizes calculated from our anchor design so we can compare strains to each other. So that's how our experiment was set up. And I want to just go through briefly some of the results that we were able to find from this. So first, we just initially looked at those stable spectral features and looked at patterns across the platforms that we studied. So here in this plot in B, we have our 5 different instruments and fractions that we looked at. And right now we're just looking at our central metabolism mutants, where each strain is in a different color. Samples that were at 0 had no spectral feature differences from our reference anchor strain, and samples that would be at 1 would have all of their spectral feature differences from our reference strain. So here we're able to see that across different analytical platforms, we are getting similar patterns for our significant spectral features, which was really reassuring. We applied this same same exact thing to our UGT mutants here in C and our natural strains here down in D. And this allowed us to see sort of the trends again across analytical groups, but then also start to identify which strains are actually the most metabolically either similar or different to our anchor strain. And within the natural isolates, we see that these metabolic trends are identical to what we would expect genomically, which was very reassuring. So this really gives us a reduced spectral feature pattern to kind of move forward with. And the last thing I'll kind of share in terms of data is how we can take that sort of narrowed list of significant spectral features and start to use this for our compound identification efforts. So this is just a simple example of the NMR polar data where we have 13 annotated compounds here on the y-axis, and then we have our 3 study groups here on the bottom with all the different strains we looked at. So we can start to see if samples are actually significantly different from our reference strain. So one example that is of biological interest is this VC1265 that has a knockout in the PYK1 mutation in central metabolism, and it has a depletion in lactic acid, which is very well supported in the literature. And then we can also see, though, then the UGT60, this strain here, has an increase in lactic acid, and then DL238, this natural isolate, has a reduction in lactic acid. And these 2 other strains, we don't have any literature to support why they may or may not have this difference in lactic acid. And it kind of gives us a sort of jumping off base to start exploring why that might be meaningful to us. And so I know I'm out of time, so I'll just leave you with this, is that using our anchor strain in design, we're able to actually track these stable features across our different platforms. Using our rigorous methods, we were able to actually provide a narrow list of features to focus on during compound identification. And I'll stop there.